Dear colleagues, I'm very glad indeed to read in Tartu and our semiotics department Professor Stuart Kauffman and to have here this seminar of the Institute of Philosophy and Semiotics. Just a few words to the beginning. My own first encounter with Stuart Kauffman was when I was a student, and when we started our seminars and further spring schools in theoretical biology. Then I happened to write to Conrad Waddington, who organized 4 symposia called Towards Theoretical Biology at Como Lake, Italy. And so he sent us 2 volumes of that. And here, among the participants, a pretty small group, photos are in this inner side. You can see Professor Kauffman, not yet professor at that time, say how he, came to theoretical biology. Now, next time, that was 15 years ago from now, in 1997 in Toronto. There was a conference on semiotics, semiosis, evolution, energy. I was there and was listening to Stuart Kauffman's plenary talk. So that means, as I interpreted it, that he has gone through a long development from now physicalist biology to non-physicalist biology. So that is what is fascinating here now, that non-physicalist biology developed in recent times in your books and writings and work. After listening your lecture, I found is in several ways equivalent to biosemiotics we are doing here in other centers of biosemiotics. However, the terminology is different. There are several differences too, but this is in a way a very interesting starting point, because just that difference makes it creative and interesting. So I hope today we can develop a little bit our conversation in that direction. But before I'll give floor to you for developing sort of logical thread. Let me ask just to tell to us a little bit about, maybe major focal points of this part of intellectual track you have gone through from physicalist biology to the current one.
Well, Kalevi, thank you. Can you all hear me all right? Can you see me all right? I have a broken foot for no good reason whatsoever. I walked too fast up and down a mountain. I don't think it's fair that you get a broken foot for walking too fast up and down a mountain, but there's nobody to complain to. But it's a very attractive boot. Okay, so I'm living with it. The first thing I want to say is thank you for inviting me. Thank you, Kalevi, and thank you for coming to listen to me. I have gone through this long passage, essentially paying no attention whatsoever to this strange field from an Anglo-American point of view called semiotics and biosemiotics. And I'm going to start by saying, and talking a little bit about why it seems so foreign to an English-American biologist's training. And then carry us forward. I only have 29 points here, which I just wrote down. So I want to tell you how I got to these 29 points before I tell you that. I've been thinking about things for a long time. But Kalevi and I have been talking in the last 2 days, and we keep saying yes to one another. Each of us gets a half a sentence further ahead, and the other one says yes. So we seem to be talking about something that we seem to agree on. And Anchi Tigler just gave a stunning lecture at the conference that we're all at this morning as a theologian. And I found myself saying yes to her. So I've tried to weave together what it was that I was so surprised about in her talk and found beautiful in these 29 points. So here's where I started. When I entered biology, shortly before I went to the Waddington conferences, Jacob and Monod had just shown that one gene could make a protein that turns another protein, another gene, on or off in the lactose operon. And they shortly thereafter published a short paper in which they said, suppose you have two genes, A and B, and A turns B off and B turns A off, then that little genetic circuit can have two steady states, A on B off, B on A off. And they therefore, in principle, solved the problem of how cells could be different from one another, even though they had the same set of genes. And that had been an outstanding problem for 70 years in developmental biology. Well, I had studied the on-off behavior of networks of neurons, and I had studied logic as a young philosopher at Dartmouth. And I asked a very strange question. I think you have to be young and naive. And in fact, I think there's a deep thing here. Trust yourself. Think for yourself about what the important problem is. Find at least one tentative answer. Then read the experts. If you read the experts first, you'll never escape them. They'll poison your mind forever. So go off on your own for a while, and then find out what the experts have to say. So the question that I wondered was the following. It was clear to everybody in the early 1960s, and I came to this 1964, that there must be some huge network of genes turning one another on and off. We thought there was maybe 100,000 genes. We now know there's 23,000. In some vast regulatory network whose dynamical behavior somehow controlled the development from the fertilized egg to the adult. And I wondered something strange. I wondered, does evolution have to work very hard to make a very special genetic regulatory network to control ontogeny, development from the fertilized egg, or are there vast classes of networks, and the whole class has the property that it behaves in a biologically plausible way, so that evolution didn't have to work so hard? I now recognize that I was asking two new questions that I'm only beginning to understand. You know, there's in Darwin, there's survival of the fittest, Spencer's phrase for Darwinism. But there has always been in the background the question of, but where did the fittest arrive from, the arrival of the fittest? And in effect, without knowing it until in the last year or so, that's what I was asking when I was 23 and 24. So I invented random Boolean nets, namely networks of light bulbs turning one another on and off. And the way to ask my question is to make classes or ensembles of networks and look for the typical properties of behaviors of random members of the ensemble and hope that they look like biology. It turns out they do. Such networks can behave in an ordered regime, a chaotic regime, and a phase transition that's critical. And so the first years of my life were spent doing that. Then I turned to fruit fly genetics. Then I turned to the origin of life. Then I turned to making libraries of random DNA, RNA, and proteins in small molecules. And then in 1995, my own transition began, Kalevi, when I wrote a book called Investigations. And it was a very strange personal adventure. I didn't know what any of you guys were doing. And I just started keeping a notebook for myself for a year, writing strands of ideas in it. And I knew that they were important. I didn't know how they would develop. I didn't know if they would come together in any form, but they did after 10 months or a year. So it became my third book, Investigations, which then transformed into my fourth book, Reinventing the Sacred. And it's just conceivable I'll write a fifth book. I'm getting a little old, but I might write a fifth book because my thoughts have gone on since 2008. So that's sort of how I got here. Can you hear me all right? Would it be better if I talked a little louder?
Yeah.
Okay. Tanan, my one word of Estonian. Okay, so let me just sort of go into it so I can get through my 31 points. Let me begin by telling us things that you all know, but to put us in the framework of why Americans think you're crazy. They don't know what you're doing, but they know you're crazy. Let's begin with Newton. So we all know Newton. I mean, what an amazing single human being. He invents the differential and the integral calculus. He invents 3 laws of motion. Bodies continue in a straight line motion unless disturbed by an outside force. Force is equal to mass times the acceleration, given the first law. And the third law, for every action there's an equal and opposite reaction. Then he mathematized those with differential equations. And then, of course, he has universal gravitation. Newton taught us how to think. He taught the Western mind how to be scientists. And we live in the shadow of Newton 350 years later. Part of what I want to do today is to take steps to get us out from under the shadow of Newton. It's an enormous shadow. But let's watch what Newton tells us. So you say to Newton, listen, Isaac, you're on first name basis with Newton. You say, Isaac, I've got a table full of billiard balls. You all know what a table full of billiard balls is. And they're rolling around. What should I do? And he says, look, Kauffman, don't be stupid. Write down the positions and the momenta, the mass times the velocity of each of the balls and the diameter of the balls. Please write down my laws of motion in differential equation form. Those laws of motion in differential equation form mathematize Aristotle's efficient cause. And then you say, okay, now what should I do, Isaac? And he said, I invented the integral calculus. Integrate the equations. Well, what's integration? It's deduction. All men are mortal. Socrates is a man, therefore Socrates is immortal. So integration yields the trajectories of the balls forever on the table, say ignoring friction or putting friction in. And because it's deduced, it's logically entailed. So Newton taught us how to think such that we get the entailed behavior, and it gave us a set of particles, and it gave us classical physics. And then to jump ahead 150 years, Simon Pierre Laplace said, if we knew the positions and momenta of all the particles in the universe, using Newton's laws, we could predict the entire future and past of the universe. And that's the birth of reductionism with Laplace, which slightly falls apart with Poincaré in 1895, when Poincaré is considering 3 planets in motion. And even Newton knew that he couldn't solve the problem of 3 planets in motion. And Poincaré showed that there's no analytic solution for the 3-body problem, and that it exhibits what we now call deterministic chaos. The importance of which is the following. The trajectories of the 3 planets, or the 2 planets in the sun, is still entirely deterministic. But as you all know, infinitesimal changes in initial conditions lead to diverging trajectories. Therefore, while Laplace thought that determinism meant predictability, Poincaré showed that that's in general not true, that determinism doesn't mean predictability. Nevertheless, the reductionist dream remains, and without spending time on quantum mechanics, in quantum mechanics you have a deterministic trajectory once again, but it's of a probability distribution. So it's still Newton's framework of thought all the way up to 1927 and the invention of quantum mechanics. Now let's turn to Darwin. What's he famous for? Well, he's famous for saying, we all know, heritable variation. There are some fitter variants. That leaves the question of where do the fitter variants come from, the arrival of the fittest, totally unanswered. But granted that there are fitter variants, competition for natural resources will lead to selection of the fitter variants. So if you have heritable variation for whatever it was that led to the fitter variants, you'll get natural selection. And the big consequence is the appearance of design without a designer. And we all know that, right? And this strand in Darwin and in neo-Darwinism and in the neo-Darwinian synthesis with the union of population genetics and Darwin, namely Mendel and Darwin, is the reigning idea, certainly in Anglo-American biology. Well, then comes Jacques Monod, who you all know, the same one who discovered that genes could turn one another on and off, in his famous book, Chance and Necessity. And Monod raises the question of teleology. Is a bacterium swimming up a glucose gradient, in some sense, knowing what it's doing? Is it acting for a purpose? And Monod says, absolutely not. This is telenomic teleonomic behavior, where teleological behavior is for a purpose, but Monod, a perfectly good mechanist in that side of Descartes' tradition of res extensa, says the bacterium is just a machine, a molecular machine, selected by Darwin's natural selection. It acts as if it had a purpose, but it doesn't have a purpose at all. Okay? So it's teleonomic. And that's the view of Anglo-American biology. So when you come along and talk about signs, American biologists think you don't know. They think you're just anthropomorphizing, that you're not being rigorous, that you're not thinking clearly. Now, I think that view of Anglo-American biology is in fact wrong, and I'm going to try to present an argument today that I hope supports what you've all been doing for all these years that I didn't know about. And it's the fun of growing together from different traditions that we may find new things together. So we commonly talk in biology about the function of something. For example, the function of my heart is to pump blood. There are no functions in that sense in physics. A ball rolling down a hill is performing no function. And we also talk about doing in biology. So we want to talk about the bacterium swimming up the glucose gradient as going to get food. There's no doings in physics. And as Kalevi and I said to one another yesterday, well, Kalevi said it, there's no meanings in physics. Where do they come from? Namely, can we find a fundamental basis, which is what I'm going to try to offer you now. You may like this or not. I'm going to try to find a fundamental basis for talk about functions, meaning, and doing. So the next thing I need to tell you is the following, and these are physical facts. Ask whether the universe has made all possible 114 atoms. The answer is yes, it has. But now ask a new question. You all know that a protein is 20 kinds of amino acids strung out in a line by peptide bonds that then folds up and, for example, acts as an enzyme. A typical biological protein has 300 amino acids. Let's ask, how many proteins are there possible? Length 200. Well, it's 20. There's 20 amino acids, so it's 20 times 20 times 20 times 20, which is 20 to the 200th possible proteins length 200. That's 10 to the 260th possible proteins length 200. Now, let me tell you something physically important. There are 10 to the 80th particles in the known universe. The known universe is 10 to the 17th seconds old. The fastest time scale in the universe is the Planck time scale of 10 to the minus 43rd seconds. If, ignoring space-like separation, the 10 to the 80th particles were doing nothing but making proteins length 200, it would take the age of the universe raised to 10 to the 39th power to make all possible proteins length 200 once. Got it? That means that in the lifetime of the universe, we will not make all possible proteins length 200. That means something physical. It means the universe above the level of atoms is on a unique trajectory. We will not make all possible complex things. That means that those complex things that actually get to exist are rather special. And I want to talk about two kinds of complex things that can exist. One are clusters of atoms, for example, low-energy structures like dust particles in giant molecular clouds, or planets, or maybe galaxies. I'm a little confused about how to think about galaxies. But I really want to talk about something else. The philosopher Immanuel Kant talked about an organized being. And what Kant said is going to be central for what I want to tell you. He said an organized being has the property that the parts exist for and by means of the whole, and the whole for and by means of the parts. So that's true of all of us. We're Kantian, I'll call us Kantian wholes. Now I want to give you a very, very minimal, simple example of a Kantian whole. It happens to be a theory of the origin of life that I came up with in 1971. And one exists, a bunch exists now. So let me just tell you about one that Gonan Ashkenazi has in Ben Gurion University in Israel. It consists in 9 small proteins called peptides. And each peptide catalyzes a reaction that glues together 2 fragments of the next peptide around a circle of catalysis. Can you all picture that? So that there's no peptide that catalyzes its own formation. The 9 peptides have the property that together, collectively, they catalyze one another's formation. So let me call that a collectively autocatalytic set. Okay? And it really works. Gonen's got it in his lab. So this is a Kantian whole. The parts are the peptides. The whole is the autocatalytic set. And now we get, I claim, for the first time, to legitimately use the word function. Because we're talking about something that's complex and gets to exist in the non-ergodic universe. Gonen's 9-peptide autocatalytic set. You are a collectively autocatalytic set. You're more than that, but you're a collectively autocatalytic set. Given a Kantian whole, we can talk about the causal consequence of a part, which plays a role in sustaining the whole, as the function of that part. And other causal consequences are side effects. So the fact that a peptide catalyzes the reaction forming the next peptide is the function of that peptide in Gonen's 9-peptide autocatalytic set. The fact that the peptide wiggles water in the nearby environment is a side effect. So, given the idea of a Kantian whole, I claim that for the first time, the notion of function has physical meaning. It means in the non-ergodic universe, that's how this thing manages to keep itself in existence. And of course, just to give you an example you all know, the function of my heart is to pump blood, but it has other causal consequences. It makes heart sounds, and if you have some medical training, it wiggles water in your pericardial sac, and they're not the function of your heart. Now, if you were to ask Darwin, Mr. Darwin, or Chuck, he'd have loved to be called. I was awarded by my secretary the Chuck Darwin Chair of Theoretical Biology, and I was very proud of it. I always thought that Darwin would appreciate being called Chuck. I don't think so. Suppose you ask Darwin, why is the function of my heart pumping blood? Why isn't making heart sounds the function of my heart? Darwin would say, don't be silly, Kauffman, Stu. You have a heart because your ancestors had hearts, and it was selectively advantageous to have hearts that pumped blood. Therefore, that's why the function of the heart is to pump blood, not jiggle water in your pericardial sac. So Darwin would give a selectivist account of the function of the heart. But Darwin's also explaining something that he didn't realize he was explaining. He's explaining my hearts exist in the non-ergodic universe. He really is. Why are there hearts in the universe? And the answer is, and Darwin just gave it to you, we will not make most complex organs. We will not make most complex organisms. We will not make most complex skyscrapers. There's an infinite sink upward in complexity. Okay, so something else to be said about Gonen Ashkenazi's autocatalytic set that's very important to me. If you call catalyzing a reaction a catalytic task or job, then the autocatalytic set, collectively autocatalytic set, achieves task closure. All the reactions that have to get catalyzed do get catalyzed. Fair enough? But no molecule catalyzes its own formation. They collectively achieve this task closure. Okay, now, let me jump ahead for a moment to the task closure in a skin cell that's dividing. So take a skin cell. Well, it's doing all kinds of things besides catalysis. It's making chemosmotic pumps. It's carrying out mitosis and DNA replication. It's making membranes. It's making mitochondria. It's making ATP. In order to divide, the skin cell, or a paramecium or a bacterium, is achieving a task closure in some enormous set of tasks. Just hold that in mind. I'll come back to it. Okay. Now we've defined the function of a peptide, and I think we can define doing. And I'm going to define doing as an external behavior of, say, a cell, which is a function. Namely, it helps maintain the Kantian whole. So when the bacterium is swimming up the glucose gradient and it gets food, it's not merely Monod's teleonomy. It's not merely as if it were doing something. It's a function. The swimming up the glucose gradient is a function, and the function is maintaining a whole in the non-ergodic universe. I want to say that legitimizes the word doing. Okay? So I'm trying to find a new basis for the language functions and doing. And yesterday, Kalevi looked at me and he said, but function is the same as meaning. And I said, yes, it is. The meaning of the peptide in Gonen's autocatalytic set catalyzing the next reaction is precisely the catalyzing of the next reaction. That's what it means to the Kantian whole. That doesn't mean the Kantian whole is conscious. It means that it's now legitimate to talk that way in the non-ergodic universe where Kantian wholes are a way that complex things can continue to exist. So that's the analysis I want to give. Okay. Now I'm going to go to what will seem like a very strange direction. I assume you all know what a screwdriver is. Does everybody know what a screwdriver is? It's this thing you screw in screws with. We all okay with screwdrivers? Okay. I want to ask you a funny question. Is there anybody in the room who can tell me all the possible uses of screwdrivers alone or with other things? Well, let's think about it for a minute. They're great for screwing in screws. They work for opening paint cans. They work for tipping up a paint can and having the paint tilted a little bit towards one side. They're superb for stabbing somebody who's trying to kill you. You can certainly use them to tie onto a stick and spear fish. You can certainly rent them to the other people and take 5% of the catch and live in a thatched hut and found capitalism on a South Sea island. You can use it as an objet d'art. Can you complete the list of the uses of a screwdriver alone or with other things? I want you to notice that you cannot. Can you feel it?
Depends on how much time do you have.
I'll give you as much time as you want. Then you think you can. See, I think you can't. Okay, so let me have the argument for the moment and then we'll argue later. I want to say that the uses of a screwdriver are indefinite in number, because I haven't told you what the other things you can use it with are. I haven't told you the possible relational features that you could use it with. So they're indefinite in number. And they're not orderable. The integers are orderable, but the uses of a screwdriver are not orderable. The first use, the second use, the third use. I mean, you could try to order them by popularity or something, but there's no natural sense in which they're ordered. I think this means something that's going to be very important to us. Because they're indefinite in number and not orderable, there is no algorithm, no computational algorithm, that can list all the uses of screwdrivers. How would you know you listed them all? It's indefinite in number. And how would you proceed to list them? They're unorderable. So I've just told you a good first example of something that's not algorithmic. And this, I think, is going to be centrally important to where our conversation goes. Now, similarly, let's take a given use of the screwdriver, opening a can of paint. Please tell me all of the things, alone or with other things, that can open a can of paint. Same problem, right? It's indefinite in number and unorderable. Therefore, you can't list them. There's no algorithm to list them. So hold on to that, and I'm going to come back to it in a minute. Because now think of an evolving cell. Now, in order to continue to divide, it has to achieve some kind of task closure. But in order to be fitter in its environment, all that has to happen is that some molecular screwdriver, alone or with other things in the cell, here's the critical phrase, find a use that increases the fitness of the cell. Then if those variant screwdrivers are heritably variant, they'll be selected by natural selection and they'll become part of the biosphere. Right? I'll come back to that. But the conclusion of what I've just said, and I could give it to you in other ways, is there's no algorithmic way to list this, and yet it's true. This happens all the time. Furthermore, selection acts at the level of the Kantian whole, not at the level of the molecular screwdriver. Right? So you can't look at the molecular screwdriver and say, you look great. You're going to make it. You got to wait, and this is terribly important. You do not know until after the fact what selection will reveal has worked. Okay, there's now a next step in this story. I was talking about this to a friend at the University of Vermont where I teach in the fall, an ecologist, Brian Beckage, and Brian said, you know, we don't have a definition of the niche of an organism. And I said, Brian, why don't we try this idea of task closure? And Brian said, that sounds like a good idea. And I went home, and then I realized the following. Wait a minute. The evolving paramecium is living in an environment, partially biotic. There's a bunch of bacteria around and other paramecia and amoebae and stuff. And partially abiotic. There's little pebbles and rocks. It achieves its task closure via causal features of its niche. Correct? Here's the critical step. The task closure via the environment that the paramecium achieves is circularly defined with respect to the paramecium. You cannot state the task closure that the paramecium under selection will find separately from what the paramecium is. They're codefinable. Okay? Furthermore, you cannot know until after the fact what the actual niche turns out to be, namely selection X at the level of the paramecium, and it turns out that, after the fact, certain strange molecular screwdrivers in the cell wiggle things somewhere in the environment that perturb some bacterium, and the paramecium can catch the bacterium more easily, and so it's fitter. I mean, maybe it makes some goo, okay, a very technical term. Let me give this to you in an economic analogy that helps me. I start a company, and I'm going to make toothpaste. And I make white toothpaste, and nobody buys it. Then I make blue toothpaste, and nobody buys it. Then I make green toothpaste, and nobody buys it. Then I make red toothpaste, and nobody buys it. Finally, in desperation, I make red and white striped toothpaste, which you may have seen on television. And everybody buys my red and white striped toothpaste. I've discovered what in American English is called my market niche, and I now know what my task closure is. My job is to make a factory that makes red and white striped toothpaste. But I didn't know till I found my market niche. It's the same thing for the bacterium. Okay? Now, this ties in a very interesting way with what Antje was saying. Because what is this that the bacterium or the paramecium is doing with respect to the environment? It's in a relationship with the environment. Precisely Antje's point today. It's making goo that makes the bacteria not move so fast, so the paramecia, which magically can swim through the goo, can eat the paramecium, so it does better. Okay? So that means that the task closure is a relational feature of the paramecium that's a meaningful one. It's a function, and it's a meaning. Yes? But everybody, we cannot prestate it. And the title of my talk is Life in Unprestatable Relationship. We cannot prestate it. So evolving life is a continuous process of finding solutions. This is where we were yesterday, Kalevi. I told you this was tying together what we talked about. It's a continuous process of problem solving where you cannot prestate the task. We cannot prestate the task. And we cannot prestate the solution, but it keeps happening. That's what's going on. It is precisely the semiotic point of view. Life is a continuous knowing of the world. Well, I should add one thing that Kalevi said yesterday. So let me just add that in. Consider cell signaling, said Kalevi. So you've got proteins that span the membrane of the cell. And some molecule binds to the outside of the cell, to the protein on the outside of the cell. Say lactose. And that sets off a cascade of phosphorylation and dephosphorylation inside the cell, and the cell does something. But it didn't have to be lactose. It could have been some amino acid or some toxin. Therefore, as Kalevi said yesterday, this bifunctional molecule, and Monod said the same thing. Monod said it's arbitrary chemically, and it is, unlike a metabolic pathway, is mediating a code. And it is this code, as you said yesterday, Kalevi, by which the cell meaningfully knows its world, in meaningful relationship to it. So life is a continuous, meaningful exploration of meaningful relationship. Okay? Now this ties into something that Antje said today that I think is very interesting. She said we can't seem to come to a physical definition of life. Let's try to define life relationally. I think she's right. Pretty good for a theologian. Even an extraordinarily smart and intelligent German, Swedish theologian. If life is a continuous exploration of meaningful relationship in solving task closure tasks in an environment, in a relationship, no wonder we can't define life just in terms of the molecules. It's not there, and I've now converted to being a semiotician of a primitive sort. Okay? Okay. Now I want to get to the most radical parts of what I want to say. I started with Newton. Now I hope I've helped legitimize what you guys have been doing for 20 years, and I hope it's useful to you. And maybe even you think that I'm right. That'll be cool. Okay? But starting in my third book, Investigations, so I'm going to tell you briefly about Darwinian pre-adaptations. So Darwin said, you know, the function of your heart is to pump blood, not to make heart sounds. But he said, a causal consequence of a part of an organism of no selective significance in one environment might turn out to be of selective significance in another environment, so be selected, and typically a new function will arise. I'll give you two examples. You have bones in your middle ear, incus malis and stapes in Latin, which I learned in medical school, that derive from the vibration-sensitive bones of the jaws of an early fish by Darwinian pre-adaptations. Now I'm going to spend a little time on a second example. Some fish have a sac called a swim bladder that has air and water in it. The ratio of air to water tunes neutral buoyancy in the water column. Paleontologists believe that the swim bladder evolved from fish with lungs, called lungfish in English, that hopped from puddle to puddle to puddle, and water got into some lungs, so now you've got a sac with air and water in it, so it's poised to become a swim bladder. So let's say the paleontologists are right. Okay? Question 1. Did a new function come to exist in the biosphere? Sure, neutral buoyancy in the water column. By the way, this is just another screwy molecular screwdriver, although in this case it's not within a cell, it's in the tissue. Okay? But did a new function come to exist? Sure. Second question I've asked, and I'm going to come back to, is did it change the evolution of the biosphere? Yeah. New species with swim bladders. They had mutant proteins, so new proteins. And then I always said, and I'm going to come back to it, what I will call a new adjacent possible empty niche. Because, see if you agree, once the swim bladder exists, is it true that a bacterium or a worm might evolve to live in the swim bladder? Yes, right? And in fact, in Africa, there are worms that live in the eyes of people, which is really uncomfortable. Okay? I mean, blech. Okay. Okay. So I'm going to come back to that. So the swim bladder, once it exists as a new adjacent possible empty niche, changes the possible evolution of the biosphere. Hang on to that. Now I want to get to the third puzzling question. Now that you're experts on Darwinian pre-adaptation, does any of you think that you could name the next 3 Darwinian pre-adaptations to occur just in human beings in the next 3 million years? Anybody think so? I'd like you to pause and try to do it. Please try to list for me the next Darwinian pre-adaptations that can happen. I want you to have the experience of your mind going blank. Can you feel it? You want me to do what? And I think I've realized what the problem is. Let me give it to you informally, then more formally. How would you name all possible selective environments? How would you know you listed them all? How would you know that you had listed all possible bits and pieces of an organism or multiple organisms, which alone or together might have the causal consequence that was the new function? You can feel that you can't. I just told you what I told you about screwdrivers. You cannot list the uses of the screwdriver, namely the selective environments. We'll argue in a moment. Okay. You cannot list the things that could open the can of paint, namely the possible Darwinian pre-adaptations. It's non-algorithmic. That's why you can't list it. Okay? Now, this means something very deep that I have pursued in investigations in my 4th book, Reinventing the Sacred. And this summer I met an amazing mathematician named Giuseppe Longo at the École Polytechnique in Paris. And Giuseppe gave a lecture in Aix-en-Provence, and he said, you know what? The phase space of biological evolution is changing all the time in ways that you cannot pre-state, which is just what I said before. We cannot say ahead of time the uses of the molecular screwdrivers in cells that will turn out to be useful. So the phase space of biological evolution changes in ways that we can't say. And we've published a paper, I'll tell you the title. It's entitled No Entailing Laws. It'll be on the film. No Entailing Laws, but Enablement, which I'll get to in a minute, but Enablement in the Evolution of the Biosphere. And it's posted on Physics Archives, and it's in press. Okay? So what this means, given the criticism that this gentleman's going to raise, what this means is you cannot write down the laws of motion for the evolving biosphere. And part of our discussion is that in physics, the phase space is always fixed, like it was for Newton, or for Einstein, or for Schrödinger, in some Hilbert space. And then they have a sophisticated discussion of mathematicians. I make the points I've made. Because you cannot write down the laws, so first is, you can't write down the laws of motion of the biosphere because you don't know until after the fact how the phase space has changed. Point one. Point two, let's suppose that the niche is like the billiard table. It's the boundary condition on selection. But you don't know what the niche is. So you don't know what the boundary condition is. So even if you could write down the laws of motion like Newton told us to do, and write down differential equations, you wouldn't know the boundary conditions, so you couldn't integrate the equations. It would be like trying to integrate the equations for billiard balls on a table whose shape kept changing in ways you didn't know. You couldn't do it. And what that means is, big conclusion one, if we're right, pending your critique, if we're right, no laws whatsoever entail the becoming of the biosphere. If so, physics and the physics worldview reaches an end at the evolution of life. And I posted on NPR in the United States a post entitled The End of a Physics Worldview, Heraclitus, a Greek philosopher, and the Watershed of Life. You see, Heraclitus said 2,700 years ago, life bubbles forth, like bubbles in a bathtub. And what's wonderful about what he said is that bubbles isn't entailed, it just bubbles forth. Well, he's right. Life does bubble forth. The universe may be governed by or described by entailing laws, but life is not. And I don't think the evolution of the econosphere is, of the economy is, to say it briefly. How did we get from Turing machines to the mainframe computer, to personal computers whose widespread sale created a niche for the sale of word processing, whose widespread sale created a niche for sharing files, whose widespread sharing created a niche for the invention of the web, where the invention of the web created the possibility of selling things on the web, and eBay and Amazon, and here we are in Estonia, and Skype, okay, and Facebook, and the Arabic Spring. Do we think that Turing or Tom Watson Sr. at IBM intended to create Facebook? No, they didn't. And I'm going to come back to that point in a moment. Namely, I don't think we can restate the evolution of the economy either. And I want to now get to a nearly last point. I want to come back to the swim bladder. I think we agreed that the swim bladder changed the possible evolution of the biosphere, because a worm or a bacterium really could come to live in it, right? So I now ask you a question you know the answer to. Do you think selection worked hard, to anthropomorphize it, on a population of evolving fish to change a lung of the lungfish into a swim bladder? Sure. Presumably selection worked hard. But did selection, quotes, work hard to create the swim bladder as a new adjacent possible empty niche in which a worm or a bacterium could come to live? No, it did not. Agreed? Selection did not strive, to anthropomorphize it, to make a new adjacent possible empty niche. But this means something magical. With no selection at all, the biosphere is creating its own possibilities of future becoming. It really is. It's creating its own possibilities of becoming, with no selection. And Darwin missed this. And I want to call this radical emergence. It's not like emergence is the collective behavior of a bunch of variables that is now familiar in the sciences of complexity. It's radical emergence of utterly novel functionalities and utterly novel ways of living. And the same thing is happening in the story from the Turing machine to the Arabic Spring. It's radical emergence. In the biosphere, we don't have to contend with human consciousness and intention, yet we have this magical, radical emergence. And the reason that I care, let me come back to the societal import of this. The early sociologist Max Weber said that with Newton, we became disenchanted. Do you know all know the word enchanted and disenchanted? Enchanted is feeling the magic of. And we entered modernity. Weber was right, and let's look at it. In the 15th and 16th century, you had the white and black magicians, the white and black magi. And the black magi thought that if you had occult knowledge and magic words, you could make nature do anything you wanted. You could turn lead into gold. You could fly. It didn't work, but they thought it, right? Then came Newton, and you had a mechanical universe. The theistic God that worked miracles was in trouble, and magic was gone. We were disenchanted. What happened? Well, in Europe we got the Enlightenment, which is the age of reason. I want to say something about that, I'll come back to it. But from the age of reason, what did it say? It said, down with the religious clerics, they're obscurantistic fools, up with Newtonian science. Why? For the ever betterment of man on a finite planet. Let's just keep having GDP growth forever, okay? It sounds a little nuts, doesn't it? But that was the Enlightenment view. And it led to the Industrial Revolution, which led to modernity and modern capitalism, and the fact that I'm sitting here with a now cold cup of peppermint tea that I can warm up in a microwave. So we've gotten lots of benefits out of the Enlightenment and in the Industrial Revolution. But we've got lots of bad things too. And I just want to comment on a couple of them. In the United States, money and power totally corrupt government. Lobbyists and contributions to political campaigns are destroying one person, one vote. I'm furious about it. We face a power structure in Europe, I don't know about Northern Europe, but in the center of Europe and in the United States, that's enormous. And Karl Marx was right. People do not give up power readily. I don't know what we're going to do about it, but we better do something or we're really in bad shape. Meanwhile, Gordon Brown, when he was Prime Minister of England a few years ago in Strasbourg, said, a phrase I think you'll understand, we're all reduced to price tags. Well, a price tag is the cost of a mop, okay? It's a little tag that says €2.27. He says we're all reduced to price tags. We are. We're all parts of this vast economic machine whose aim is forever growth and gross domestic product. And if you ask why, so I have a phrase for this, it's very American. We really are making, selling, and buying purple plastic penguins for the poolside. I don't have a pool, but I don't want a czar telling me that I can't have a purple plastic penguin for my poolside. I mean, I might. But why? Why are we making purple plastic penguins for the poolside? We are. We're making all kinds of stuff. Why? And I think part of the answer is we don't know what else to do. We really don't. And that's why, Kalevi, I was telling you that I'm becoming fascinated by living in different cultures. You've been here, I thought it was 10,000 years. Kalevi tells me it's 11,250 years since the Baltic dropped by 50 meters, and that you have a calendar. I don't believe that part, but anyway. 11,000 years ago, you didn't have Skype and you were doing pretty well, right? And I love Skype, okay? So we know the good and bad of the Enlightenment. And the cultural, civilizational part of what I want to say, and then I'll end, is if it's true that there's no law that entails the becoming of the biosphere or the economy, and if it's true that the biosphere with no selection creates its own possibilities of becoming, we have a chance of being re-enchanted. It's magic. How much magic do you want? It's magic, okay? Now, not everything is good, but there's a way in which what becomes is generous. We can, in some sense, often fix what goes wrong. It's the arrival of the fitter again. So I'm going to end with my own view about a task that I think confronts the people under 40 in the room. Those of us who are over 40, it's too late. We might help. Some kind of global civilization is going to emerge. We have 30 global civilizations around the globe. They're being crushed together. As they are, the roots of their civilizations are being threatened. They are retreating into fundamentalisms that are hostile and often lethal. If you don't think so, look at the Arabic world, or in America at the religious right, or at Hindu fundamentalism. It's fear that's driving this, of the disruption of a way of being in the world. So what do we want for the world that you younger people will create? We could be, forgive me, all American and eat hamburger. I like hamburgers. We could all speak Chinese and eat chow mein, or something much more magical. In the United States, in New York, you can buy Chinese Cuban cuisine. Now, I love that. I mean, I don't know what it tastes like, but I think it's really great, okay? Where it doesn't touch our cultural roots, we can invent new cultural forms, because we're not afraid. I think we need to learn to touch one another gently enough to protect our cultural roots, but firmly enough to invent new cultural forms that allow us to be human in ever more diverse ways. And I want to finally end with a dream of mine. The American essayist Emerson wrote about what's called Emersonian perfectionism. And what he said, we must live the well-considered life. And what Emerson and Thoreau meant in the 1830s in Boston was, you're born with a set of strengths or virtues. Spend your life cultivating your virtues so that you become good at them. They're your natural strengths. What's wrong with it, I think, is the following. I haven't quite said this. You see, remember when I asked you if your mind went blank? And I think you agreed that your mind did go blank. That means something really deep. It means that not only do we not know what will happen, so let me make it explicit. Let me flip a coin 10,000 times. And I want to calculate whether it'll come up 5,223 heads. Can I do it? Sure, I take the binomial theorem and I calculate it. But notice that I knew ahead of time all the possibilities. All heads, all tails, everything in between, right? So I knew all the possibilities. I didn't know what will happen, but I did know what could happen. Yes? All known probability theory begins with a statement of what all the possibilities are and constructs a probability measure. It might be the frequentist interpretation of probability. But for the becoming of the biosphere, we agreed that we couldn't say what the next 3 Darwinian preadaptations are. That means that we do not know what can happen. Not only what will happen, but what can happen. And Turing and Tom Watson Sr., when he said we're going to need 3 computers, didn't know about Facebook or Skype, right? They didn't know what can happen. Governments act as if they know what can happen and they can optimize. If we do not know what can happen, and I'm 2 sentences or 4 sentences from the end, if we do not know what can happen, then reason is an insufficient guide for living our lives. Then how do we do it? We've been doing it. When I first thought of this, I thought, oh my gosh. Then I thought it can't be that bad. We've been doing it for 3.8 billion years. Then I thought, I don't deduce my life, I live it. So we need more than reason. The reason of the Enlightenment is insufficient, Kalevi. It's insufficient. We need much more. And we have it, otherwise we wouldn't be here. And I think it includes intuition and metaphor and a lot of other things. And it leads me to the last thing I'm going to say. There's more, well, gosh, there's one more thing I want to just mention. And it's the following, that I fall in love with the idea of living the well-discovered life. You see, the well-considered life is like a hotel breakfast here in Estonia. And everything's laid out, you know, and you go in and you get some eggs and sausage and salmon and whatever. But it's there on the table, and you know what it is. Life's not like that. You don't know what may open before you as you live your lives. What if we take as a high good in human life as living our well-discovered life? Now, I just want to mention one truly final thing. If the becoming of the biosphere is not entailed, how do we do positive science beyond entailing law? And it's another 20 minutes to tell you about that. But the summary of it is, it's how Kantian wholes make their worlds together. And I think it's semiotic. They make meaning together. But the meaning isn't just meaning, it's the conditions of the very existence of the things in the non-ergodic universe. Thank you.